expansion. Then in between heartbeats, the aorta elastically recoils and drives that stored volume of blood down the aorta in between heartbeats. So that elasticity in recoil is crucial because it acts as a second pump in parallel with the ventricle. So you've got the ventricle pump, aorta expands. A ventricle relax, aorta contracts. And that second pumping mechanism of the aorta allows or causes continuous blood flow down your aorta between heartbeats. The flow pulse slows down, but it continues to have forward flow throughout the whole cardiac cycle. So I've hopefully convinced you that these are really interesting tissues, heart valves and aorta, specialty composites of elastin and collagen that are put together to make them extensible, flexible to undergo this cyclic loading, but also strong enough to resist overexpansion and rupture. Now, you probably realize, and everybody realizes, both of these types of tissues can fail under different disease conditions or sometimes with overloaded mechanical conditions. And that's where my interest really comes in. I was interested in these tissues as an engineer because I wanted to see, these are remarkable functional tissues where we can't engineer anything like them. I want to understand how the elastin and collagen works, how it's put together to produce these amazing mechanical properties. But beyond that, I'd like to know how this tissue, is it able to adapt to changes in mechanical loading conditions? Are these soft tissues, can they be thought of as a smart material, an adaptive material that senses and responds to mechanical loading conditions? If you look at the literature, there's lots of research studies that have looked at alterations in the structure and the mechanical properties of heart valves and aorta and arteries under different pathological conditions. So we know a lot about how the heart wall changes its structure and mechanics in heart failure. We know how heart valve leaflets become floppy and weak in heart valve pathologies. We understand how artery walls become stiffer and thickened in hypertension. But I was wondering, is there not any conditions where these tissues undergo an adaptive response, not a pathological response, but a beneficial adaptive response to changes in their mechanical loading conditions? And as an engineer, we have lots of examples of these kinds of smart materials. And in engineering, there's a list of a bunch of them. And basically all of these materials have the ability to sense and respond. And when I say respond to external stimuli or external conditions. And that response is in some way beneficial. In engineering materials, it's beneficial by design. You change the conditions, your smart material will alter their properties in a way to adapt beneficially to that. And it seemed to me that soft tissues in the body should also be able to do the same thing. We do have evidence of this. If for instance, if you repeatedly lift weights, your muscles will remodel and adapt to that mechanical loading. You can weight train, you can remodel your muscles, you can remodel your heart with long-term, physical exercise. And so there is some information about that. But what I have been particularly interested in are some of the other normal physiological adaptations that involve changes in mechanical loading in the cardiovascular system. And this is during development, as the fetal and newborn animals develop, their cardiovascular tissues develop, blood pressure increases gradually over gestation, and the growing tissues adapt and develop to that increased blood pressure. And it's very easy for growing tissues to do this because, the cells are building new tissues, and they can take those mechanical changes and modulate their the tissue synthesis in order to match those loading conditions. So there is some information on that, but I was interested in mature cardiovascular tissues. Is there not any examples of mature heart valves, aorta, responding to mechanical loading conditions that are beneficial? And the one place in the literature where this was all missing was pregnancy. And so I had to learn a lot about pregnancy. I was coming out of my engineering PhD, and I just sort of knew a little bit about pregnancy, about the maternal circulation, all these changes happening in the maternal circulation. So I was reading about it. And then, of course, here's a picture of me. This is exactly 12 years ago, almost to the day. And I understood now firsthand the incredible changes that happen in the maternal circulation during pregnancy. Blood volume increases, the heart stroke volume, the volume pumped out with every cardiac cycle. The cardiac output goes up 50%. So basically, this is called a volume overload condition. Very quickly, early in pregnancy, you have 50% more blood circulating in the body, which is remarkable. So accompanying that is a structural expansion. And this is seen in, imaging studies in human patients. Women who are pregnant have an increase in size of their heart, and their aortas widen. And so that to me seemed really interesting. That's clearly an adaptive response of the maternal cardiovascular tissues. But I want to know, what are the collagen and elastin doing? How are they sensing these changes? Are they changing the mechanical properties of the tissues in an adjustment to these loading conditions? And I discovered there was almost nothing in the literature about this. I will add here, because I came at this looking at this from an engineer, I see, okay, cardiovascular tissues undergo volume overload. It's purely a mechanical stimulation that's going to create adaptive remodeling. And I did understand in my reading along the way that this is superimposed on all the hormonal changes that happen in pregnancy that can also trigger tissue remodeling. So I'm just putting that little note in there as an aside. Just to give you an example of some of the changes in cardiovascular conditions that happen in pregnancy, this graph here shows the change in cardiac output versus gestation. So this is change from pre-pregnant conditions. And you can see a very rapid increase in cardiac output during gestation that reverses postpartum. So here's full term, and you have an increase, a change in cardiac output, an extra nearly 2 liters per minute coming out of your heart. What's really interesting is that these changes are all augmented in your second pregnancy, and the changes are augmented even further in your third and fourth pregnancy. So your heart becomes ever increasingly larger in subsequent pregnancies. So there's something interesting about this adaptation to pregnancy, that it's like the organ has a memory of the past pregnancies. Whatever is going on there, we have no idea. But I wanted to just show you how the magnitude of these adaptations change with subsequent pregnancies. So here's my overview of what I was interested in. Cardiovascular remodeling in pregnancy. We've got a mechanical overload, which I was focused on, superimposed on hormonal changes. I want to know, do these tissues adapt as a smart material? Can they adapt their structure and mechanical properties? Well, I already mentioned we know the heart does this. And this is just some pictures to show you that the heart remodels in pregnancy in a way that is distinct from pathologies. So here's a picture of hearts from mice, from a non-pregnant and a pregnant, late pregnant mouse. And you can see the the ventricles cut on cross section. You can see the adaptation, the enlargement of the ventricles. And this is in contrast to pathological cardiac remodeling. So like I mentioned, we understood how the heart adapts, and this cardiac adaptation is beneficial. But I wanted to see what are the heart valves and what are the aorta doing. My hypothesis was that the volume overload would cause elevated mechanical stresses on those tissues and trigger structural remodeling. So my long-term questions were, what are the structural changes underlying cardiovascular tissue remodeling in pregnancy with focus on the heart valves and aorta? Does the remodeling alter the tissue mechanical properties? And finally, is this remodeling reversible postpartum after birth? So the model I've chosen, the model I'm using is really the only one available to us. In order to be able to study cardiovascular tissues from never pregnant and pregnant animals, we take advantage of the fact that cattle are sent to slaughter. Some cattle happen to be pregnant when they're sent to slaughter. And farmers don't know this. They load cattle onto the cart or onto the truck and they're sent to the abattoir. And you know, they don't know their pregnancy state until after the animal's slaughtered. So I can use this, take advantage of this by going to an abattoir and collecting hearts and aortas from cattle that have never been pregnant, my control group, and cattle that happen to be pregnant at slaughter. And I can even, if I collect the fetal calf and measure its crown rump length, I can calculate the gestational age of the animal. So this is an animal model that gives me hearts that are big, aortas that are big, from various points along gestation that I can calculate based on the fetal calf. So my first question, I wanted to know, what do heart valves do and what do aortas do? And I was at this conference in Sydney, Australia in 2004, and there was a session on heart valve remodeling. And there was a session on heart valve mechanics and heart valve replacements. And there was quite an argument breaking out between two parties of researchers. One who said heart valves should have an intrinsic ability to remodel, just like any other soft tissue. And then the other half of the room said, no, heart valves are just collagen flaps. They have no sensing mechanism for tensile or shear stresses. They're just passive flaps of collagen. So I was sitting in the audience thinking, okay, this is the first thing I'm going to do when I get back to Canada, is I'm going to start collecting hearts from pregnant and never pregnant cattle, and I'm going to start looking at the valves, the heart valves. And I remember one of the main researchers in our area, I told him this on the way out, and he said, heart valves don't remodel, but he said, even if they did, you'd never see it in the mitral valve, because the mitral valve is so large, etc. The structure is so complicated. So I went home and I started collecting mitral valves. And so there's a mitral valve leaflet that we had taken out of a cow heart, laid it down. So this is the leaflet laid flat. And again, it's just a flap of collagen. It's got some elastin in there as well. So these are quite flexible flaps of tissue, but if you overexpand them, they become very stiff and strong. And here you see the heartstrings, those chordae tendineae that attach the underside of the leaflet down, and these would attach into the ventricular wall. And they would be pulled under tension every time the left ventricle contracts. So we started by just laying these things out, measuring their size. How big is the leaflet? How many tendons are attached to it? And we counted all those things. And then we did all kinds of structural analyses that I'm not going to get into, but looking at the structure of the tissue, what the cells were doing, and the particular structure and waviness of collagen and elastin. And then I took samples of the heart valve and did mechanical testing on them to test things like the valve stiffness and extensibility. And just to show you a snapshot of what we found with our heart valves, here's our picture of isolated heart valve leaflets from never pregnant cattle So here's an aortic valve leaflet, the mitral leaflet, one of the pulmonary, and the